Welcome to the 14th lecture for Chemistry 312. This is the lecture on plutonium chemistry. It is in 3 parts. The readings for all parts are listed here. The plutonium chemistry chapter, in the chemistry of the actinides and transactinides, and challenges of plutonium chemistry. This is a compendium of information on plutonium that was collected by Los Alamos National Laboratory. Both of these readings are linked to the web page. Part 1 of the plutonium lecture series will cover nuclear properties and isotope production of plutonium. We'll have discussion of plutonium in nature, and this is actually naturally occurring plutonium, very small amounts, and we'll discuss that. We'll talk about plutonium solution chemistry. We'll see that there's similarities in some trends of the actinides, where we'll have the plutonyl species. But unlike what we discussed with uranium and neptunium, plutonium is primarily tetravalent in solutions, although it can have oxidation states from 3 to 6 in solution, which makes the chemistry challenging and interesting. We'll also talk a little bit about separation and purification of plutonium, and then part 1 will end discussions with the atomic properties of plutonium. Part 2 will discuss the plutonium metallic state, which is an example is shown here. This is a metallic ring of plutonium that's made by an electrochemical process, and we'll discuss that. And the third part of the plutonium lecture will cover plutonium compounds. We'll start off the lecture discussing the different isotopes of plutonium. There are isotopes of plutonium from as low as 228 to as high as 247. Some of the important isotopes include plutonium-238. Plutonium-238 is made from the neutron capture of neptunium-237. That produces neptunium-238. That beta decays. That produces plutonium-238. This was the route by which plutonium was identified. This relatively short-lived alpha-emitting plutonium-238 has a high specific activity and is relatively easy to observe. The plutonium-238 is separated from the neptunium-237 target by ion exchange. You can also obtain plutonium-238 by the decay of curium-242. This isotope, since it's a relatively short-lived alpha emitter, has a lot of energy associated with it, about half a watt per gram. So this is used as a power source for space exploration. You can make plutonium-238 oxides with up to around 84% plutonium-238, so that you can have some plutonium-239 in there. As this oxide form, they actually enrich the oxygen in oxygen-16 to limit neutron production. If you have a nucleus with that extra neutron, for instance, oxygen-17, the alpha-N reaction, the alpha particle hitting oxygen-17, producing a neutron, has a relatively large cross-section. You want to limit the amount of neutrons coming off your source. And if you make the plutonium dioxide, you'll have a power source of about 0.4 watts per gram. You can make 150 grams of plutonium dioxide in an iridium container, and that will produce this heat, and the heat can be converted to electricity. And this is what's used on a number of spacecraft for missions to planets beyond Mars. It's also used on the Mars rover and the Curiosity for a power source. Another plutonium isotope is the well-known plutonium-239. As we discussed in the course already, this is a fissile isotope. The heat generated from plutonium-239 is much less than you would see for plutonium-238, owing to the longer half-life of the 239 isotope. The information related to critical masses of plutonium-239 is shown here, where a critical mass of plutonium can be as low as half a kilogram under these solution conditions. Of course, a solution condition where the neutron is thermalized, the reaction cross-section increases. That is why these critical masses under these thermal conditions are much less than either the oxide or the metal. There's also a natural component of plutonium that's in the environment, and some of these can be found in ores that contain a lot of uranium. And if you think about uranium, you have uranium with a very small spontaneous fission half-life. So uranium can emit neutrons from the spontaneous fission. If you have ores with a large amount of uranium, such as the Cigar Lake uranium deposits, you have a probability of this neutron, or these neutrons that are emitted from the spontaneous fission, capturing onto uranium-238 and creating plutonium-239. In some of these materials, the ratio of plutonium-239 to uranium has been evaluated. And remember, over here, this is 1 part in 10 to the 12th. So 6.4 times 10 to the 12th, looking at this sort of ratio. So this definitely indicates that you can find plutonium-239 in nature, but it's at extremely low concentrations. There's also been some papers written about plutonium-244 in nature, and this is based upon spontaneous fission of plutonium-244 and the xenon isotopes that would result from that. And the reason for this even being a probability is the relatively long half-life of plutonium-244. And these isotopic ratios have been examined in bastenosite minerals. These are the same mineral phases that are found, that are used in lanthanide mining. The solution chemistry of plutonium has some similarities to what we've seen with uranium and neptunium, in that there's a number of oxidation states available. Now with plutonium, you can have 5 oxidation states from the 3 to the 7. However, in solution, you can actually have the 3, 4, 5, and 6 coexisting together. The 3 and 4 tend to be more stable in acidic solutions. The 5 has prominent stability in neutral environments, and the 6 in more basic solutions. In the literature, there is some evidence of plutonium-8. However, experiments tend to disagree with each other, so there's no concrete evidence on the existence or chemical states of plutonium-8. Plutonium spectroscopy is shown here. We'll start off with this picture of the different colored plutonium solutions. These are all the tetravalent plutoniums. As we see, we have different colors as a function of the ligand, HCl, so chloride, perchlorate, nitrate, there's plutonium colloid. And then here's different colors as a function of oxidation state, 3, 4, 5, 6, and 7. Obviously, if we have different colors, we would expect to see different UV visible spectroscopy, and this is evidenced by the absorbance spectra of plutonium in perchloric acid for plutonium-3, plutonium-4, plutonium-5, and plutonium-6 primarily. What I want to point out for these different oxidation states, there are peaks which are indicative of the oxidation state. For instance, plutonium-6 has this absorbance at 830 nanometers and a molar absorptivity of 555. Plutonium-4 has a peak at around 650, and another peak around 730, and these molar absorptivities are on the order of 35 and 60. One of the more interesting aspects of plutonium solution chemistry is the number of redox states that can be in solution at the same time. The oxidation potentials are close. They're all about a volt for the 4 common oxidation states. So these are shown here, plutonium 3, 4, 5, and 6. In the acidic system, you see the potential is all about a volt. This permits coexistence of oxidation states. Now there are some trends. For instance, plutonium 4 and 5 will tend towards disproportionation, and here's an example of the 4 in the presence of water going to the 3 and the 6 with some proton given off. So if you wanted to prevent this disproportionation, you could have lower plutonium concentrations, since 3 plutonium-4s are needed, or higher acids that would, from Le Chatelier's principle, would shift the reaction towards the reactants. And here's an example below of plutonium-5 going to plutonium-3 and again plutonium-6. So these kinetic changes are a function of conditions including pH, ionic strength, and plutonium concentrations. An example of the change of a plutonium oxidation state as a function of conditions is shown here. Here we have the change of a plutonium-4 oxidation state or a plutonium average oxidation state being plutonium-5 is a function of pH. This shows, depending upon what you would start off as your stock solution, with the potentials given on the previous slide for your different plutonium redox couples. You could use that information to make a certain stock solution. Then, as a function of pH, this would be how the speciation for the oxidation state would change. And there's an example of the kinetic influence, starting at either pH 1, an average oxidation state of 4, or pH 3, an average oxidation state of 5, how the mole fraction changes as a function of moles, seconds, so concentration and time coupled together. Here are routes for producing different oxidation states of plutonium. These can be coupled with the redox information that was shown on the previous slide. General route of making a given oxidation state, if you wanted a stock solution that was just one plutonium solution. If you were to make a 3 or a 4 plutonium oxidation state, you would take your solution, reduce it to the 3, for instance, using hydroxylamine. Then if you wanted to make it to the 4, oxidize that up. Conversely, if you wanted to make the 6, oxidize everything to the 6. Ozone's a very good route for doing this. And then if you wanted to make the 5, reduce the 6 to the 5. So as we've just discussed, the oxidation state of plutonium is very important. It's important to control it and at least to understand it. And understanding what the oxidation state could be can be enhanced by evaluating what can change the redox behavior. So plutonium can undergo redox by actinides. This is similar to disproportionation. And the rates have been assessed compared to other actinides. So for instance, reduction of plutonium-6 by tetravalent actinides proceeds over pentavalent states, so it goes from the 6 to the 5 to the 4. These reactions tend to show a hydrogen dependency. This hydrogen dependency, that means acid. If acid is produced, you could make sure your plutonium's in a acidic environment to limit any change in redox. Ligands, for instance, these organic ligands here can wind up stabilizing some lower oxidation states, such as plutonium-4. Things that are reduced or oxidized through single electron transfer, such as the single electron reductant, they tend to be rapid. So reduction by iron 3 tends to be a rapid route for changing the oxidation state of plutonium. And then there's complexation can change the stability of different redox states. So carbonate medium is going to behave differently compared to perchloric because the carbonates will bind the plutonium effectively where the perchloric will not. And then there's also disproportionation, such as plutonium-6, where it can this can be reduced, and then that reduction be complicated by disproportionation. And then there are some reducing agents that are used in the Purex process, hydroxylamine with hydrazine, production of nitrous acid in nitric acid. It's used to, the hydroxylamine is used to reduce the plutonium from the 4 to the 3. However, plutonium-3 can be oxidized, producing this nitrous acid. It adds this nitrous acid to the system, which can run an autocatalytic reaction. So if I produce this, I can wind up reducing my plutonium down. One of the things we also see is this autoradiolysis, where the fact that plutonium is radioactive and it's forming radicals and redox agents due to this radioactive decay. These reactions tend to be low if concentrations are below 1 molar. If it's in a nitrate medium, for instance, you can form nitrous. You can also, if you form peroxides, as we talked about with other actinides, you can form peroxide species. So the autoradiolysis, just a change in the redox, is really rate proportional to plutonium concentration and dose rate. So the plutonium concentration and dose rate, those are also saying something about the half-life of the plutonium isotope that's in solution. Data for plutonium hydrolysis studies are available. The hydrolysis constants are listed here, and over here is shown for different plutonium oxidation states, a CHES calculation. But basically, plutonium is going to behave as other tetravalents or other metal ions where the tetravalents are going to form the strongest hydrolysis complexes. And for the tetravalents, plutonium forms very strong hydrolysis components. A more full picture of different oxidation state calculations are presented here. This can be useful for understanding stock solutions, both concentrations and pH range. For instance, if one looks at plutonium-3, if you had a plutonium-3 stock solution, you could go up to pH of around 6, and the plutonium would still be the free metal ion. Whereas plutonium-4, under the range examined with a 10 millimole solution, the dominant phase circled here is for the plutonium dioxide, in other words, plutonium precipitate. Otherwise, the oxidation states are similar to the behavior of other metal ions, where the 5 does not show hydrolysis until around pH 7 or above, and the 4 is in some ways similar to the uranium compound, where you get the hydrolysis around pH 4. One of the consequences of the strong plutonium hydrolysis of the tetravalent state is the formation of colloids in solution. As we saw on the colored test tube solutions, plutonium-4, the polymer is a different color, and the UV-Vis data also shows a different result. Here, plutonium-4 colloids have a higher absorbance at the lower wavelengths under the conditions examined, whereas plutonium-4 in solution just shows a characteristic absorbance peak at around 475. So these colloids in solution can be thought as extended hydrolysis products, actually extending all the way down to the dioxide. These particles are between 1 and 1,000 nanometer in size, depending upon the route of the experiment. X-ray diffraction shows that this plutonium-4 colloids are similar in FCC structure, so face-centered cubic structure, to plutonium dioxide. So the theory is that they're fundamentally small plutonium dioxide particles in solution. One could think of this as partially hydrated, so the plutonium can be coordinated with oxygen, hydroxide, or water. And you can think of it as going from the watered, the aqua species, to the hydroxide and oxide species. So there's a kinetic component associated with the formation of colloids. Characterization of colloids can be done with a number of different techniques: small angle neutron scattering, light scattering, laser-induced breakdown spectroscopy. Each of these tend to produce different results as far as the characterization of plutonium colloid particle sizes. That has to do with two things. One, the methods themselves. For instance, light scattering is predicated upon spherical particles. And two, the solutions are different. The time when the solution was made and when the measurement was made will vary. Therefore, the results can be varied. Some plutonium XAFS data is shown here. They do demonstrate the average face-centered cubic structure, being somewhat overly simplistic but reasonable. And what can be seen here is that the data, this is data for plutonium dioxide. This is what the structure would look like, nice and organized and patterned. We see this from the XAFS data. And then if we look at the plutonium colloid structure, we see that there's a number of peaks between this plutonium oxygen and plutonium-tonium bond distances that are measured by XAFS. In the colloid system, these additional peaks are indicative of added plutonium-oxygen bond distances. What we do see is similar is the plutonium-plutonium bond distance from both these data being around 3.83 angstroms for the plutonium dioxide and 3.84 angstroms for the plutonium colloid structure. So this data and these computations do give credence to the plutonium colloids being an extended oxide-type species. And again, this is driven by the strong plutonium-4 hydrolysis properties. General plutonium aqueous chemistry follows oxidation trends, as you would expect for any metal ions, where tetravalent plutonium generally going to have the largest complexation constants, and pentavalent plutonium for a given compound is going to have the lowest complexation constants. The 6 and the 3 oxidation states can be relatively close to each other. And similar to other metal ions, their behavior with oxoanion complexants, oxoanion ligands, is trends similar to other metal ions, where the perchlorates very weakly interact and phosphates strongly interact. Plutonium-4 can have very high coordination numbers, 7 to 12 ligands around the metal center. Example of some specific plutonium species, an important one is the carbonate. It's shown here. This is for plutonium-5 or plutonium-6, in this case plutonium-6, where we have the plutonium oxo species, and the carbonates coordinate around the equatorial metal center. 2 oxygens from the carbonates coordinate, so it's a bidentate coordination. This is similar to what is observed with the uranyl species. And the X-half data is used to produce some bond distance between the plutonium double bonded oxygen, plutonium oxygens from the carbonates, and then some other distances, plutonium carbon and this plutonium outer oxygen. Plutonium-3 species, as the carbonate rapidly oxidizes to the tetravalent state. The complexation constants for the plutonium-3 can be modeled on americium-3 species. Plutonium-4 carbonates can have a large number of carbonates coordinating from 1 to 5, and this carbonate coordination increases with pH and carbonate concentration. Plutonium-5 carbonates can be formed by the addition of plutonium-5 to a carbonate solution or the reduction of plutonium-6. Often you'll get the mono and tris carbonato species, and plutonium-6 carbonates are really just an extension of the uranium-6 system. One of the differences being is that the distances between the plutonium and the oxygen are a little bit smaller compared to the uranium system, and this is due to the actinide contraction. The plutonium nitrates are very important species, particularly due to their prevalence in reprocessing and separations. Really some of the first solution compounds evaluated. They have the coordination chemistry is similar to the carbonates, where you can get bidentate and planar geometry, but unlike the carbonates, the compounds have much weaker interactions. There tend to be 1 or more nitrates in the inner sphere. Plutonium-3 compounds have been prepared but are somewhat unstable. The plutonium-4 species can have nitrates from 1 to 6 coordination. It's found that the tris and pentacarbonatal complexes are not as prevalent. The complexation constants have been evaluated spectroscopically. And the anionic species, for instance, this plutonium 6 nitrato -2 species, is an important species for anion exchange. However, sometimes if you look in the literature, it's unclear if it's the penta or hexanitrato species for plutonium-4 that's driving anion exchange. The nitrates can also be formed and precipitated from nitric acid solutions. So high nitric acid solutions with high plutonium concentrations can form precipitates, which are these neutral species with water coordination. And then mixed species can be formed, for instance, tributyl phosphate with plutonium nitrate in the organic phase. There's no evidence of an inner sphere plutonium-5 nitrate species, so that's a very weak complex. And only the plutonium-6 has been truly identified, complexation constant-wise. The mononitrate has been identified for plutonium-6 in solution. But obviously, if you have ion exchange of plutonium-6 in nitric acid solutions, you're forming more than the mononitrate. A range of plutonium sulfates have been evaluated, including plutonium-3, where you get mono and disulfate complexes, the solid potassium plutonium sulfates with water have been prepared. Plutonium-4 has high affinity for sulfate complexes. Again, both mono and bis sulfate complex solution species have been formed. The plutonium-5 species is not well characterized, and like the plutonium-4, the 6 forms the mono and bisulfate from acidic solutions. And this compound has been examined by both optical and IR spectroscopy with solid plutonium species produced. Phosphate complexes have extremely low solubility. There's a range of species, so the characterization is difficult. And this has to do with the fact that the ligand is also changing. The phosphate can have a number of different forms. So plutonium-3 has not been characterized, but the compound has been proposed. Plutonium-4 exhibits a wide range of phosphate complexes. Again, these tend to have very low solubility, so forming the plutonium-4 species in solution is a good way to remove it as a precipitate. There's some evidence of the plutonium-5 phosphate, and plutonium-6 phosphates have been found with a number of different species, a number of different metal ions coordinating with the complex. The peroxides, as was mentioned earlier, for uranium and also earlier in this lecture on plutonium chemistry, forms interesting compounds as shown here. The peroxide can also be used to change redox state, for instance, oxidizing from the 4 to the 6. There is no confirmed structure of this plutonium bridge species as shown here. This is the proposed structure. However, it is known that you can form the peroxide precipitates and they will incorporate surrounding anions. So this is also similar to the uranium. A route for precipitating plutonium in a solution for separations is the use of the peroxide. Carboxylate-containing organic acids are also important plutonium species. You can get single or multiple carboxylate ligands. They can form strong complexes with plutonium, and they have the typical oxidation state trend. For plutonium, they tend to stabilize the tetravalent states. So for plutonium-3, if you form carboxylate complexes, you will get oxidation of plutonium from the 3 to the 4, and you can get a range of mixed species. For instance, with EDTA, the degree of protonation of the EDTA, the ethylamine diamine tetraacetic acid, will vary depending upon the pH. And also you can get mixed hydroxide species, so you can get plutonium hydroxide with EDTA. Plutonium-4, as we already mentioned, is stabilized, and you can form these compounds, and plutonium will stay in solution at relatively high pH. And if you remember looking at the speciation diagram of plutonium-free metal at any sort of pH, you tend to get a precipitate. However, if there's a carboxylic based ligand in your system, you can have solution phases. So for instance, ethylene diamine tetraacetic acid or diethylene triamine pentaacetic acid, they formed a 1-to-1 ligand to metal complexes with plutonium. There's a range of mixed species that can be observed. So for instance, plutonium with a hydroxide and a DTPA. And these ligands, EDTA, DTPA, citric acid, other carboxylic based organic acids, can be used for the dissolution of plutonium oxides or hydroxides. Plutonium-5 compounds with carboxylic based ligands tend to be unstable, and they'll undergo oxidation or reduction depending upon the solution conditions, and the plutonium-6 species have been observed. Plutonium carboxylate complexes, these organic acids, are also very important species for the nuclear fuel cycle. They tend to form strong complexes and stabilize the tetravalent oxidation state. And here's an example of the carboxylic functional group, where R is just a hydrocarbon of some sort. So an example of this would be something like EDTA, ethylene diamine tetraacetic acid, or DTPA, diethylene triamine pentaacetic acid. Any organic acid, though, with this functional group will have these similar properties. Plutonium-3 carboxylate species tend to oxidize to the 4, and a range of species have been identified, including mixed hydroxide species, so you may have a plutonium bound with a hydroxide bound with this carboxylic acid. The plutonium-4 species tend to be stabilized by complexation with carboxylic acids, and the compounds tend to be 1-to-1, for instance, plutonium EDTA, plutonium DTPA, and these these compounds with these acids can be soluble in pH solutions under pH conditions where the free plutonium is precipitated. So, for instance, at pH 5, you can form an EDTA plutonium compound that'll be in solution, whereas the free metal ion would just be a hydroxide or precipitate species. For this reason, compounds like EDTA are used to dissolve plutonium-4 oxides or hydroxides into solutions. The plutonium-5 compounds are unstable, and they will oxidize or reduce depending upon the solutions. And plutonium-6 species are similar to the uranium-6 species. They've been observed, and they've been used for solubilizing plutonium. Other compounds that are in solution include the iodates, which have been precipitated. They are not well characterized, but they have been prepared by hydrothermal methods. The perchlorates, the perchlorates generally are used for non-coordinating systems. There's no pure solution or solid phases characterized. Most likely does not form interspheric complexes. And then the oxalates. The oxalate is a very common ligand used to precipitate plutonium. They form microcrystals, can be formed with plutonium. The 4 and the 3 form precipitates. The 3 forms with 10 to 6 waters, and the 4 can form with 2, 4, and 5 oxalates with a given number of waters, anywhere from 0 to 6. As with other organic acids, the plutonium-5 tends to disproportionate, and you can form the plutonium-6 oxalates in solution, and they will precipitate. Plutonium halides have also been extensively studied. This is related to plutonium separations and metal formations. Data is presented here, so number of species, the given reactions, the complexation constants, and the Gibbs free energy. So all this information for the fluorides, the oxyfluorides, chlorides, bromides, iodides listed here can be used to understand, predict, model the behavior of plutonium halide species in solution. And similar to the uranium eel species that we discussed, you can have cation-cation complexes using the plutonyl species, so plutonium-5, plutonium-6. So you can form compounds that bridge over the eel oxygens. This has primarily been examined for the neptunyl species, but it has been observed between uranium-6 and plutonium-5 in 6 molar perchloric solution. The reason you want the 6 molar perchloric solution, the perchlorates are not coordinating. So this is a relatively weak complex, but if we have a solution where the ligand is weaker, we can form the compound where the plutonyl here coordinates, the oxygen coordinates to the metal center on the uranyl. The plutonium chemistry we just described is useful for separations of plutonium. Here's some data on plutonium separations. About 2,000 metric tons of plutonium has been produced. The production rate is shown here, between 70 and 75 metric tons per year. Large-scale separations of plutonium is primarily based upon the Purex process, which we've discussed and will be presented in more detail as in other courses in the summer school. There's also some non-aqueous pyroprocessing methods, which are responsible for the formation of solid-phase plutonium species through electrochemical reduction. One of the first separation techniques for plutonium was the bismuth phosphate method. This is a precipitation-based separation, where precipitates of bismuth phosphate in acid, they carry tri- and tetravalent actinides, so the tri- and tetravalent actinides will precipitate out with the bismuth phosphate. This is done by taking the tri- or tetravalent oxidation state of the actinides with a bismuth nitrate and phosphoric acid solution. The solids are then separated. If you oxidize this, the plutonium will oxidize from the 4 to the 6, become solubilized with the other trivalent actinides remaining in solution. These solids can be used. This can be used as purification methods, and things like lanthanum fluoride precipitation of trivalent and tetravalent actinides can be used to further purify the plutonium-6 in solution. As we've already discussed, solvent extraction, plutonium is well known with tributyl phosphate, part of the Purex process. There's some interest in third phase formation. There's some literature on this and links into the website. Ion exchange and extraction chromatography are also well known for separations of plutonium. These are more laboratory scale separations. Some trends can be based upon oxidation state. So plutonium 3, 4, 5, and 6, imagine they have different oxidation states. And this would be sorption onto a strong base anion exchange resin, an HCl. So for instance, the plutonium 3 is not absorbed, and the 4, 5, or 6 are sorbed at different HCl concentrations depending upon their oxidation state. So this could be a route for purifying plutonium by sorbing it to an anion exchanger, reducing it, and upon the reduction to the 3, the plutonium is released. Another example is shown here where we have some of the different plutonium oxidation states. The plutonium-6 sorption has very high properties on this Dowex resin, so this would be an anion exchange resin, whereas the 4 also has relatively good sorption properties, but less than the 6. In general, cation exchange trends for plutonium, the nitrates, sulfuric, and perchloric acid show stronger influence than the HCl. And there's an increase in distribution coefficients in perchloric at high acidities exhibited for plutonium-3 and plutonium-4. Like uranium hexafluoride and uranium hexachloride, the plutonium, fluoride, and chloride hexavalent species are also volatile, and this can be used for plutonium-based separation. As an example is shown here, where the dioxide of plutonium is placed into a fluidized bed reactor with fluorine at 400 degrees. Other fluorinating agents, for instance, this ammonia bifluoride or this fluorinating compound, can also be used as opposed to just fluorine gas. The resulting hexafluoride species is volatilized. When this enters a thermal decomposition column, the hexafluoride plutonium species reduces to the tetrafluoride, which is not volatile, and the formation of fluorine gas. And this is a way of achieving a separation and a recovery of the material. Supercritical fluids have also been examined for the extraction of plutonium. Most of the supercritical fluids evaluated have been carbon dioxide. And this supercritical fluid is also evaluated with a complexation using ligands such as tributyl phosphate, deanyl trifluoroacetone. This has been studied for extracting plutonium from contaminated soil. One could extract these systems with the ligands binding the plutonium, pulling it out of the soil. And then when the supercritical fluid enters normal atmospheric condition, the solution, the supercritical fluid, goes to a gas phase, and what's left behind is plutonium with the ligands. So you can achieve this separation and a concentration of plutonium from these, for instance, this soil system with a supercritical fluid just by using atmospheric conditions. This concludes the first part of Lecture 14, the lecture on plutonium chemistry. This lecture covered nuclear properties and isotope production, some discussion on plutonium in nature, plutonium solution chemistry, separation purification, and atomic properties. Part 2 will cover the plutonium metallic state. Please continue with that part of Lecture 14.